dielectrics and capacitance. Okay, so dielectrics and capacitance. So here, first of all, in order to know about the concept of capacitance, so from the lower standards of the class, we know that, so see here, for a capacitance, we are having one parallel plate of plus charge, and here you are having one more parallel plate of negative charge. In between, you are having some medium, and that medium is nothing but what? Dielectric medium. So definitely, so if you want to know the behavior, how the if you want to know the behavior of capacitance, so you should have an idea regarding the dielectric which is in between these two plates. So the value of capacitance will change with respect to dielectric medium. Will change with respect to the dielectric medium. So therefore, we have to understand the behavior of the electron in dielectric materials. Okay, so see here, if you observe carefully, suppose if this is one plate which is of plus charge, and again you are having one more plate of thickness, some thickness is there. Okay, so this is negative charge. Here you are having three different mediums. So this is conductor, and here also this is also conductor. In between you are having dielectric medium in between. So see here, electrons, they are flowing from conductor and entering into dielectric medium. So this is one kind of phase. And again, the electrons, after entering into the dielectric material, they are entering from dielectric medium to conducting medium. Again, this is of another phase. Some capacitance, they may have more number of layers of different dielectric materials. So let it be dielectric material 1, dielectric material 2, dielectric material 3. So if in such type of capacitance, so see here, electrons are moving from one dielectric material to one more dielectric material. So since the traveling of electron is happening conductor to dielectric material and dielectric to dielectric materials, as well as from dielectric material to conducting material, you should know how these electrons are being behaving in different kinds of medium, in different mediums. So once if you know the conditions to be fulfilled by the electrons while traveling from one medium to another medium, then we can go for the understanding of the capacitance. That is the reason why we are going for the first with the dielectrics, and later we are going to see the capacitance. Okay, so that is an important introduction for this chapter, that is nothing but dielectrics and capacitance. And one more thing, that is capacitance is current dependent. So therefore we will go with what? First we will learn about the concepts of current, and later we will go with current densities, and finally we will go with dielectric boundary conditions. So this is very, very much important. You can have 5-star for this dielectric boundary conditions in this chapter, and later finally we go with the calculations of different capacitors. Here you can expect one essay type questions under the type of different capacitors, and here from you can expect dielectric boundary conditions. If not, they go with the current densities. Okay, so gunshot questions. In this class, first we go with the current. What do you mean by current? Basic definition of current and basic representation of current equation. And later we are going to see what are different types of current densities are there. Okay, so if time exists, then we will derive the first equation for first type of current density. Okay, first type of current density. So don't worry with the next class of EDC. So since EDC sir is having some health issues, he is unable to take the class. Okay. So meanwhile, within a short period of time, we can close the session as early as possible if you complete all the topics much easier. Okay. So fine. First, we go with the first concept of this chapter, that is the basic definition of current. You people very well are very much familiar with the definition of current, that is so rate of flow of electrons. Rate of flow of electrons. These electrons are nothing but what? Charges. So simply to define the current, that is I is equal to rate of flow of electrons or charges. Charges, that is Q. Rate of flow. Rate in the sense we are talking with respect to time. So therefore Q by T, or simply that is dQ by dt. dQ by dt, which is defined as a definition, basic definition for a current. So I is equal to Q by T or dQ by dt. Okay. So now what do you mean by current density? So this is the next density term. So already you have seen about electric flux density and as well as electric charge density. Okay. So electric flux density as well as that is you have seen, and now you are going with the current density, and it is represented by J. Okay, it is represented by J. So any density, I told that, so whatever the density you are going to take, you are going to take the total value of that density. Here you are going to take, since you are going to take the current, that is total current per unit length or unit surface area or unit volume. Okay, so or unit volume. So this is the definition for the current density. The current density is the total current per unit length or per unit surface area or per unit volume will give the value of current density. But here we are with respect to current density, we are having three types of current density. So these types, whatever the current densities are there, so these types are classified with respect to the flow of current. With the flow of current, how this flow of current is happening, So with respect to that, these current densities are being classified into three types. The first one is known as convection current density, and the second one is known as conduction current density, and the third one, which is known as displacement current density. So these are the three different types of current densities, and how they have been classified. So they have been classified based on how the current is flowing. So in order to understand this concept of current density, here I'm going to take one real-time example. So if you know how the heat is transferred. So you can relate the same how current is transferred. Here, heat is also transferred in the form of convection as well as conduction. So heat can be transferred in the form of a convection as well as conduction. So that means here convection and conduction, if you understand the terms, so similarly you can understand the flow of current in the form of convection as well as conduction. Conduction in the sense, so see here, for example, if you take a vessel, and inside if you are having water in it, if you want to heat that water, what you are going to do, so you are going to place that vessel under a stove, and you are going to keep one under, you are going to have the flame. So here the flame is directly contact. Here the flame has direct contact, and the water is also in direct contact with the vessel. So the flame will get whatever the heat is available in the flame, it gets transferred to the vessel, and the vessel after get heating up, whatever the substance is there which to which we want to heat up, that is nothing but the water. That water is also in direct contact with the vessel. So such type of transfer of heat, okay, such type of transfer of heat is nothing but what? Conduction. So here there it is nothing but what? There will be a direct contact. If the flow of heat is through direct contact, then such type of flow of heat is nothing but what? Conduction. And next, see here, one more type of flow of heat is there. Here you are having sun, and here you are having air. So sun is a very good source of heat, and we are receiving that heat. Whatever the person is there, he is experiencing the heat of the sun without direct contact. Okay, so here the flow of heat is by means of medium. Here we are not having direct contact with the sun. We know that what will happen if you are having direct contact with the sun. Okay, so therefore here the flow of heat is in the medium, but here since there is no direct contact of heat, of direct contact between the source and the destination, and here the transfer of heat is happening in the form of convection. In the form of convection. So similarly, we can relate these two examples. Okay, so these two examples with respect to flow of current. So flow of current, direct flow of current, that is nothing but, suppose if you are having one conductor in which you are having electrons. These electrons are traveling from one point A to the point B, which they are having a direct contact with the conductor. And such type of flow of current within the conductor is nothing but what? Conduction. Within nothing but the flow of current inside any conductor is known as what? Conduction. And when comes to the convection, so see here, for example, you are having clouds. Okay, so here you are having clouds, and here you are having the air. So during the lightning time, whatever the charge that are present inside the cloud, so they are going to have in the form of a light. They are going to form in the form of a light and enter and pass through the air. Pass through the air. So see here, here the clouds are acting as one kind of conductor, one plate, and earth is acting one more plate. In between you are having air as a medium. Okay, so forming a capacitance, forming a capacitor. So here, since there is no direct contact between the clouds and the air, but here the flow of charges are happening. Here the flow of charges are happening. So such type of conduction, such type of flow of current or flow of charges is called as what? Convection type of flow. convection type of flow. That means the flow of electrons inside air or vacuum is considered to be what? Convection type of current. So one more example also I can tell. So that is we are having CRT television, picture tube television. Okay, so here you are having one television. If you open it, you are having one picture tube like this. Here you are having one cathode. Okay, so here inside this tube you are having a vacuum. Okay, inside the tube you are having a vacuum. So when you are sending a when you switched on this TV, the flow of electrons will happen inside this tube, and they are going to hit this tube, and you can see the picture. So here also the flow of electrons are happening inside this vacuum tube, and here you can also call this type of flow of current is nothing but what? Convection type of flow. So convection type of flow of current. Okay. So here that is the thing. And the third one, which is known as what? Displacement. Third one. So displacement current densities. This thing you can have with respect to semiconductor flow of current. So here in any semiconducting material, the flow of currents are done by using diffusion. That is nothing but by using poles and holes. So plus and minus, so they are going to have one depletion layer. You people are very much familiar with this concept. Okay, so depletion layer, these electrons have to be transformed from if you want to have the flow of current, definitely this depletion layer has to be zero. So here the diffusion of electrons are going to take in place between these depletion layer. This concept already you people are learning in case of EDC subject, and later you also will learn under power electronics, so that in the case of third year. Okay, so in such type of semiconducting material, the type of flow is going to happen in case of what? So displacement current density. Okay, so these are the three different varieties of flow of current. With respect to the flow of current, okay, so here the densities are classified, that is convection current density, the first one, and the second one, which is known as conduction current density, and the third one, which is known as displacement current density. So in this session, we are going to see about the convection current density, and we will close this session right now. So a very small derivation, just a matter of 2 to 3 steps. Okay, so you guys no need to worry for that. So first we will go with the first basic current density. So the first one, which is known as convection. So current density. So current densities, they are represented by J. So with the final expression, we have got whatever the final expression. By looking at the final expression, we have to differentiate whether it is a convection current density or conduction current density. But for all the current density, we are having a common term, that is what? J. So for that, I already told that convection type of flow is nothing but flow of electrons inside vacuum or within A. So that here I'm going to take one vacuum tube. Okay, so of length L, which I have placed that vacuum tube along x-axis, along y-axis. Okay, so here I'm making one arrangement. So this is a vacuum tube. Of length L. So this is a vacuum tube. So here I have placed that vacuum tube along y-axis. Okay, so through which we are sending electrons, and these electrons are traveling with velocity v, which is nothing but capital V. Okay, so capital V. Now instead of taking for entire length of this vacuum tube, I'm going to consider a small part of it. Okay, so I'm going to consider a small part of it, and I'm going to draw that small part. So this is the tube where we are concentrating just right now. Okay, so just right now. See here, since this is along y-axis, so therefore, out of total y, we are considering a small part of it. So this is dy, and we know that what is the coordinate system. So this is y-axis, and this is x-axis, and height is z-axis. So therefore, this is dy. And what about the inclined line? The inclined line will become dx. What is the height? Height is nothing but dz. Okay, so dx dy dz. And if you multiply dx dy dz, you will have what? Volume of dv, volume of dv, and within this volume, you are having a charge density that is nothing but rho v. Volume is small v, velocity is capital V. Okay, so please don't get confused. So small v is volume, capital V is velocity. Okay, small v is volume and capital V is velocity. Okay, so now we are going with the derivation for convection current density. Okay, convection current density. So since we are talking with respect to density, a small volume we have considered of dV, which is having of rho v. So therefore, we will start with that point. Charge density given by rho v, given by rho v, that is equal to what? Charge density is dq divided by dv, dq divided by dv. And now if you do the multiplication, that is taking dq on one side, and so therefore you will get rho v into d. And we know the formula for differentiable volume in rectangular coordinate system. See why I have gone with rectangular coordinate system. See here. So whatever the shape here it is there, whatever the shape it is there, so it is forming what kind of coordinate, and it is forming rectangular coordinate system. So therefore we have gone with rectangular coordinate system. So in differentiable volume, the differentiable volume for rectangular coordinate system is given as dv is equal to what? Dx dy dz. So dx dz. So therefore substituting this formula, so dq is equal to rho v dx dy into dz. So dq. Now see here, observe on one point. Here, see the electrons are entering through this surface. Electron, they are entering through this surface, and they are leaving through this surface. They are leaving through this surface. So if you want to write with respect to surface area, so we have to make the concentration for these two surfaces only. These two surfaces. So these two surfaces areas, they are having the value of small area of ds. So see here, they are having same equal area. So if you calculate for one, so that is enough. So what will be the value? So this value is length into depth, length into height. So what is the length? The length is given as d. What is its length? The length is dx. And what is the height? So height is dz. So what is the surface area will become? So now the surface area ds is equal to what? So dx multiplied by dz. So now in this formula, you are having dx as well as dz. So now I am replacing that value with ds, that is nothing but what? Dx into multiplied by dz. So this is equal to rho v small v. So rho v ds multiplied by what? Dy. So what is the value? So this is dq. Okay, so now I am taking the value of ds under this. Okay, so I'm going to take the value of ds, but before that, I'm going to differentiate the value. Whatever the equation is there, so let it be equation 1. So equation 1, differentiating equation 1 with respect to dt on both sides. So therefore, what will be the value? So dq divided by dt, that is equal to rho v ds dy divided by dt. dy divided by dt. So see here, dq by dt, that is nothing but what? So charge per time. Charge per time is nothing but rate of flow of charges. That is called as what? Current. That is nothing but what? Current. So replacing that value with what? Current, that is di. Replacing the value with current as di. dq by dt is nothing but current. So therefore di, that is equal to rho v ds. See here, y by t. Y is nothing but what? Y axis. Y axis, we are going to measure the y axis with respect to meters. Let it be 10 units or 10 centimeters or 1 centimeter, like that we are going to have the distance. Y will give distance in dy by dt. Y is distance. T is nothing but time. Distance per time, we are going to call it as what? Velocity. Meters per second. Units per meter per second is nothing but what? Velocity. So dy by dt is distance per time. So you can have the value as velocity. What is the velocity? It is capital V. So di is equal to rho v given by ds, that into v. So now I'm making the value, I'm bringing the ds value to the denominator side. So di by ds, the value is equal to rho v multiplied by capital V. What is di by ds? Di by ds is nothing but, see here, what is current density formula here? Current density formula here, total current per surface area. So total current, if it is di, surface area if it is ds, now I can replace the value of di by ds with what? With j. With j. So therefore, so di by ds will become j is equal to rho suffix v multiplied by capital V. So which is the formula for convection current density. Okay, in convection current density we will have velocity. So how to identify? How to identify whether this is a convection current density or conduction current density? So in convection current density formula we will have velocity. Okay, we will have velocity. So this is all about current densities and convection current density, and remaining current density, that is conduction current density, that we will see in the next coming session. Okay, so we will see the conduction current density in next coming session. So this is all for today. So today we have learned many things. Okay, so please try to take so most probably today I will upload all the videos. Okay, so try to download them and have the notes. That's all for today, and remaining concepts we will see in tomorrow's class. Okay. I hope Naushad, you have sent attendance for me. Okay, okay, I have got it. So anyhow, guys, thank you for today, and see you tomorrow.
Sir,
Thank you.
class extend చేసుకోమన్నారు సార్.
What? Young Naushad?
సార్ గుడ్ మార్నింగ్ సార్. ఏడీసీ సార్ ఇప్పుడే కాల్ చేసి ఒకవేళ సార్ తీసుకుంటారని తీసుకోమన్నారు సార్.
Okay, okay. So that's why I have continued. Okay, so
Shall we continue, sir?
So already we have learned many things as for today that will be overloaded for you. It's not good
Okay, sir. Okay, sir.
in a single session. So that's why we have covered most of the topics, dipole, electric dipole, remaining all the things. So it's not good to have more concepts in a single session. Okay, so remaining things we will cover next session regarding this. Okay.
Thank you, sir.
Okay, sir. Thank you, sir.
Okay, then thank you for today.